So I will show B-jet energy regression that we developed for the CMS experiment at the LHC. So I know we've already heard a couple of times what LHC is, but for people who just joined, let me just give you a quick summary. And for the experts, you can just look at the beautiful mountains here that we can see from Geneva on a good day. So the LHC, or the Large Hadron Collider, is the largest and the most powerful collider ever built. So it consists of a 27-kilometer ring of accelerating magnets that accelerate protons to nearly the speed of light, which are then further collide at the 4 interaction points where we have our detectors. So our detectors are like giant cameras that record particles that emerge from the collision. And here you can see the picture of the CMS detector. And when I say giant, I really mean it, because as you can see the scale here, it's 15 meters tall, 30 meters long, and weighs about 14,000 tons. So let me just briefly sketch the physics that we do at LHC and how we extract it. So here's the LHC tunnel where the protons are accelerated and then they collide. And then our detectors surround these interaction points where the protons collide and then effectively record all the particles that emerge from this collision. Then we analyze this data we get from our detectors, and we can reconstruct events happening. By looking at these reconstructed events, we can infer the underlying physics that led to such an event. Right, so the underlying physics is described by the standard model, well, and beyond, that describes particles and their interactions, and our detectors detect all of these particles. So here's just to give you an overview what you're seeing here. So the detector has an anion structure, so it really completely surrounds the interaction point and is hermetic, and then it consists of several sub-detectors that are designed to detect different types of particles. Right. So the goal of the event reconstruction is to assign each energy deposit and each track in our detector to individual particles. Then from this reconstructed particles, we can reconstruct the full event kinematics and infer what underlying physics led to such an event. So we go from a mess of particle hits to a reconstructed event like this. And then if we were lucky, then we can discover something really cool like the Higgs boson that we discovered in 2012 and that led to a Nobel Prize. So here you can see an event display from our detector. So it's a real event display from data recorded in 2017. So, and it's a cross-section of a detector, so you can see like a mess of different tracks in the middle here where the collision happens, and then 2 tracks going upwards and downwards. So those tracks are left by particles called muons, which are kind of like electrons, but about 200 times heavier. But looking at this event display, you can sort of think, well, these particles are probably not too hard to reconstruct. You can kind of see like a just quite clear track going through different detectors. So probably we can handle that. But some particles are actually quite a bit harder to reconstruct than others. For example, quarks and gluons cannot exist as free particles, and when they're produced, they create sprays of tens of different particles that we call jets. So here is an event display of this jet from our detector, and you see that it has really 20 different tracks produced by different particles that are coded here in different colors, and also different energy deposit in our colorimeters. So to reconstruct this jet, we have to reconstruct all of this information, so all of this energy deposits and tracks. So then we have jets that are rising from big quarks, called B-jets, that are special, and they're especially challenging to reconstruct. And that's because often these B-jets decay to a final state with a particle called neutrino, which is a particle with such feeble interaction that leaves the detector undetected. And then they also originate from a secondary displaced vertex, and on top of it, they tend to spread radially over a wider area, so which means that some of the energy will be leaked outside of this cone that I showed you at the previous slide. So all of these properties will lead to an underestimation of this B-jet's energy and thus degradation of its resolution. But the important thing is that these B-jets are actually very important for many physics analysis that we do at LHC. So the better we can reconstruct this B-jet energy and estimate their resolution, the more sensitive we are to the underlying physics that we are actually interested in. Right. So here's the idea. We want to implement a multidimensional regression to infer the true B-jet energy from this reconstructed detector information that we have. So I will present the B-jet energy regression that we developed for the CMS. So I've implemented it in a deep neural network and trained it on a large simulated set of B-jets. And it was designed to improve the resolution of B-jets and based on their composition and properties. And the improvement that we got by using this regression helped us to reach the milestone observation of the Higgs boson to gate to bottom quarks that was announced last year and even made it to the front page of the physical review letters. So the idea is we're trying to infer the true energy from the reconstructed detector information. So we first generate a very large set of B-jets, 100 million B-jets, and then we pass them through the detector simulation. So why do we do this? Because this way we can have both information, so we can have a true information at the generator level where we have the true energy of the B-jet, including all of these escaping particles that we can't detect. And then we also have all of the reconstructed information that we can actually get from our detectors. So then, of course, for the inputs to our training, we use the reconstructed information, and we combine such information about jets as the kinematics and the different constituents. So here is the same picture of the jet that I showed before. So we will use the information from the tracks, secondary vertices, individual energy deposit reconstructed by different subdetectors. We will also look at the composition and the jet shape. So we will try to understand how wide the jet is, what kind of particles are carrying most of the energy, and basically everything that we can get from our detectors about these B-jets we will use. Then for the target, we of course need to target the true energy. So it would be the true Monte Carlo energy with all this missing energy from this neutrino particles included. So then our target will be the ratio of this true energy and the reconstructed energy. Right. So what is our task? Our task is to get the energy correction to improve the resolution, but also to provide a jet resolution estimator per jet. So per each jet, we can say how well it is reconstructed. And so to get the correction, we can use an Uber loss function. So here is the resolution distribution shown here. So we'll use Uber loss function to get the correction. What about the resolution estimator? So if you look at this plot, we can say, okay, if we know the position of 25, let's say in 75% quantiles, then the resolution estimator can be estimated as half difference of those. So then we add to our loss function the two quantile losses, and then the joint loss function would be the Uber loss function plus two quantile loss functions. So we implement this in the feed-forward fully connected neural network that takes 40 input features, the ones that I described just before. So we construct all of the observables from all the tracks and energy deposits and all of that, and feed this to the neural network, and then the outputs is the correction and the two quantiles from which we construct the resolution estimator. So we use the backpropagation uses stochastic gradient descent with atom optimizer, and we train this network on a single GPU. And now let's talk about the results. So how can we evaluate the results? So well, we should look first of all at the energy scale. So we look at the ratio of this true energy to this reconstructed energy before and after the regression. So we look at it as a function of different kinematics and also at the different quantiles. So here on the top plot, we look at the scale as a function of the pseudo-rapidity, and different lines show different quantiles. And what we see is that after the regression is applied, the distribution gets narrower and have flatter response. But let's now quantify this improvement. So to quantify it, we want to compare the relative resolution. So the resolution normalized to the most probable value of your distribution. So here we'll look at the relative resolution before and after regression in red as a function of the jet momentum. And we see that inclusively, the resolution is improved by about 13%, and then it depends a bit on the phase space. And we perform very similar, we get very similar performance for B-jets from different physics processes, which, of course, that's what we want to see. So now, what about this resolution estimator? So as I mentioned, knowledge of this resolution estimator on jet-by-jet basis would be really beneficial because it can be exploited in different physics analysis that search for a resonant production of these B-jet pairs. What I mean by this is, like, for example, if you have a particle that further decays to two B-jets, you will reconstruct the B-jets, and from these B-jets you will have to infer the information about the particle that decayed to them. So for this kind of analysis, knowledge of the jet resolution is very important to increase their sensitivity. But for this reason, it's also very important that the resolution estimator that we get as an output from our network is that actually correctly represents the jet resolution. So to check this, we should look at the correlation between the intrinsic jet resolution that we can estimate using the Monte Carlo truth information and the resolution estimator that we provide. So here on this plot, you can see this correlation, and it's shown inclusively for an inclusive sample of B-jets in dark blue, and then for different samples with jets with different momentum. And you can see that we have a very nice linear dependence that confirms that our resolution estimator correctly represents the jet resolution. So now we can use this information in different searches. So far I've talked about the resolution improvement that we get per single jet, but as I mentioned, many analyses use the mass of a particle that decays to let's say, two B-jets, that is the discriminating variable for a signal extraction. So let's take an example, the Higgs boson that decays to two B-jets, then this mass of the Higgs boson will be a discriminating variable because it will have like a nice Gaussian kind of structure for the signal, and then in the background it will be like exponentially falling background. So the better your resolution is in this mass, the better you can actually discriminate signal from the background. So here is the part of a relevant display. So you can see this two blue dark areas. So those are the B-jets, and they're actually coming from the Higgs boson that you can't see, that you only can understand that it is coming from a Higgs boson when you reconstruct everything. And if you look at the dijet mass before and again and after regression, that you can see that the resolution improvement, we get a resolution improvement of 20%. And this is a significant improvement that helped us to reach this observation of the Higgs decay to bottom pairs. And now the last but very, very important point is that so far I showed you this nice improvement on Monte Carlo, but the question is, can we actually transfer this improvement to the real LHC data? And this point is very important because if we don't get the same improvement in data, we can't really use this technique, because this way we might bias our data and eventually discover something that doesn't exist in data. So that's a no-go. So to check whether we get the same performance in data, we select a high-purity sample of events with a B-jet and a well-reconstructed Z boson in data. And why such event topology is because in this event topology, the Z boson and the B-jet are back-to-back, which means that the ratio of their energy should be around 1. And then the better the resolution of your B-jet is, the narrower this ratio, the distribution of the ratio of the PT, the momentum of the jet, and momentum of the Z is going to be. So then this variable is called PT bounds, and we can evaluate the performance in data using this variable. So we extract the sample of in data of B-jets, and here you see the distribution of this ratio of the two momenta before and after regression, and if you look at the relative resolution improvement, we get it of 13% in both Monte Carlo and data. And this is a very important check because we see that this resolution improvement that we achieve in Monte Carlo actually successfully transferred to the domain of real data. And that already brings me to the summary. So we developed this B-jet energy regression using the deep neural network for the CMS experiment. We trained it using jet structure and composition information, and we provide the energy correction and the resolution estimator. We validated on data that was recorded by the CMS experiment at the LHC, and we already successfully applied this technique to help to reach the observation of the Higgs boson. Thank you.
Thank you. Questions? I do have one. You said you use the tracks as inputs. You don't use individual tracks, but rather quantities based on the tracks.
Yeah, we construct the variables. So we never really use individual particles. We really try to construct all possible observables from all the information we can use. Yeah.
Okay.
So we will also look whether the track is coming like from a muon or electron. We will use all of this information, but we will not look at the individual.
So you have a fixed number of input features.
Yeah. So yeah. We don't like rely on individual particle flow candidates now.
Okay.
Do you see further room for improvement, or you think you squeezed out everything?
So far it looks like we did squeeze out everything we can, because we, like as I showed here, we used the feed-forward architecture, but we also tried with different architectures, and we can't really get any more improvement from here. So I think it's most likely no. I would be very happy to see an improvement, but so far, no.
Thank you. Question in the back. No, you cannot shoot.
Yeah, I mean, I think you covered this, but maybe I didn't understand completely. What is the risk of, since you're training off Monte Carlo data that is a standard model of physics, what is the risk that using that trained model, you miss something in the actual experiment that is not in the Monte Carlo?
Well, so what we do here, we're not trying to like look at some specific different event reconstruction. We really just reconstructing the jets. Like we know everything about jets, at least we think we do.
Can you move to the phone?
Sorry.
Microphone.
Yes. So here we use basically everything we know. So if we pose questions like this, then I think we will go really all the way to the very basic event reconstruction we do at CMS. Like we do different kind of searches, making as little assumption as possible. But when we talk about jets, we normally assume that we know what they are. Yeah.
Okay. So thanks a lot, Nadia.